Picture yourself standing on the deck of an offshore oil platform in the middle of the North Sea. The wind is screaming at over 100 miles per hour. Waves the size of apartment buildings are crashing against the steel legs beneath you, sending walls of white water 50 feet into the air. The entire ocean looks like it's boiling. The horizon has disappeared behind a curtain of rain, so dense you can barely see your own hand stretched out in front of your face. Lightning splits the sky every few seconds. Thunder arrives almost simultaneously, so loud it rattles your teeth. And yet, beneath your feet, the platform barely moves. The lights stay on. The crew continues working. The drilling operation may not even pause. How is that possible? How can a structure sitting in the middle of one of the most hostile environments on Earth survive forces that would tear apart almost anything else humans have ever built? The answer involves some of the most extraordinary engineering ever conceived, material science pushed to its absolute limits, and a deep understanding of how the ocean actually behaves at its most violent. If you have ever stared at footage of an oil rig in a hurricane and wondered how on earth it stays in one piece, you are in exactly the right place. If this kind of content blows your mind the way these storms blow across the ocean, hit that like button right now. Drop a comment below telling me what you think is the most impressive part of offshore engineering, and subscribe so you never miss another video where we break down the incredible science hiding in plain sight all around us. Now, let's get into it, because the full story is far more fascinating than most people ever imagine. The first thing you need to understand is that there is no single type of oil rig. The word gets used as a catch-all term, but the offshore industry actually uses several completely different types of structures depending on water depth, weather patterns, and the economics of a particular field. Each type has its own strategy for surviving storms, and understanding those differences is the foundation of everything else we're going to talk about. The most recognizable type is the fixed platform. These are the structures you probably picture when someone says oil rig: towering steel or concrete legs anchored to the seafloor, with a large deck of equipment and living quarters sitting high above the waterline. Fixed platforms work brilliantly in relatively shallow water, generally less than about 1,700 feet. Their strategy for handling storms is almost brutally simple. Be so massive and so deeply anchored that the ocean simply cannot move you. A large fixed platform can weigh hundreds of thousands of tons. Its legs can be driven dozens of feet into the seabed. The structure is designed not to flex out of the way of wave energy, but to absorb it, to resist it, to outlast it through sheer overwhelming solidity. These platforms are not trying to dance with the storm. They're trying to stand completely still while the storm exhausts itself against them. But fixed platforms have an obvious limitation. The deeper the water, the longer and heavier the legs need to be, and at a certain point the engineering becomes completely impractical. This is where compliant towers come in, a kind of hybrid approach. Compliant towers look similar to fixed platforms from above, but their design philosophy is almost the opposite. Rather than resisting wave energy through rigidity, a compliant tower is engineered to flex. The structure is designed to sway slightly in response to wave and current forces. This controlled flexibility dramatically reduces the structural stress that builds during a major storm. Think of it like the difference between a thick, rigid oak tree that can snap in a powerful wind and a young bamboo plant that bends dramatically but springs right back. The compliant tower is the bamboo. It yields just enough to survive. Engineers designed the natural frequency of the tower swaying to be well outside the frequency range of typical ocean waves, which prevents the nightmare scenario called resonance, where a structure begins swinging in sync with an outside force, and the oscillations build until something catastrophically fails. Then you get into the floating structures, and this is where the engineering becomes almost surreal in its sophistication. Semi-submersible platforms are probably the most visually striking of the floating designs. From a surface, they look like a conventional platform deck sitting on pontoons. But the real engineering magic is what is happening underwater. Those pontoons extend deep below the ocean surface, connected to the deck above by massive columns. And here is the crucial insight that makes semi-submersibles so extraordinarily capable in severe weather. Wave energy is not uniform through the water column. At the surface, waves are violent, chaotic, and massively energetic. But as you go deeper, the energy dissipates rapidly. By the time you're 40 or 50 feet below the surface, the violent churning you see up top has calmed dramatically. The lower hulls of a semi-submersible live in this relatively calm deep water. The deck lives high above the worst of the wave action. The columns connecting them are deliberately narrow, offering as little surface area as possible to the waves crashing around them. The result is a structure that achieves remarkable stability not by being rigid and immovable, but by placing most of its buoyancy deep enough that the ocean's surface fury simply cannot reach it effectively. To maintain position without anchors in very deep water, these floating platforms use a technology called dynamic positioning, which is genuinely one of the most impressive achievements in the history of marine engineering. A dynamically positioned vessel has no anchors at all. Instead, it uses an array of computer-controlled thrusters mounted at various points around the hull to actively counteract every force the ocean applies to it. Sensors measure wind speed and direction continuously. Acoustic systems on the seafloor track the vessel's exact location. GPS provides additional positioning data. Gyroscopes measure the vessel's orientation in 3 dimensions. All of this information feeds continuously into a central computer system that calculates, dozens of times per second, exactly what thrust needs to be applied or to keep the platform within an acceptable radius of its target position. During a major storm, the thrusters may be running at significant power for days, fighting wind, current, and waves simultaneously to hold the platform steady over the wellhead far below. Drill ships represent another floating approach. These look, as the name suggests, much more like conventional ships, with a drilling derrick rising from roughly the center of the vessel. In very severe weather, a drill ship has an option that a fixed platform obviously does not. It can simply disconnect from the well and sail away. The disconnection procedures are carefully engineered, allowing the drill string and riser pipe to be safely pulled from the well and sealed before the vessel moves off. When the storm passes, the drill ship returns, relocates the wellhead using acoustic transponders, and reconnects. It is an elegant solution, and it reflects a broader truth about offshore engineering. Sometimes the best way to survive extreme conditions is not to be there when they arrive. The physics of what the ocean actually does to these structures is what makes everything else make sense. Ocean waves are not random chaos, though they can look that way. They're the product of wind energy being transferred into water, and they follow patterns that engineers and oceanographers have spent well over a century learning to describe mathematically. In the worst storms in the North Sea, significant wave heights can reach 60 feet or more. In the Gulf of Mexico, during a major hurricane, similar values have been recorded. But individual rogue waves can be dramatically larger than the expected maximum. The famous Dropner wave, recorded by instruments on a North Sea platform on New Year's Day, 1995, had a measured height of approximately 84 feet in a sea state where the expected maximum was around half that. Platforms must be designed with margins that account for these statistical monsters that the ocean produces rarely, but inevitably over the lifetime of a structure that may operate for 30 or 40 years. The materials used in offshore construction have evolved dramatically over the decades. Today's structures use high-strength steel alloys specifically formulated to maintain toughness and resist brittle fracture even at the low temperatures found in deep, cold ocean water. Every critical weld may be inspected using ultrasonic testing or radiography to detect any internal defects before they can cause problems. Because the most insidious long-term threat to an offshore structure is not any single storm, but the cumulative effect of millions of smaller wave loadings over years and decades. Every time a wave passes a structural member, it bends the steel slightly. Steel can tolerate an enormous number of such cycles before a crack begins to form, but the number is not infinite. Engineers calculate the fatigue life of every critical structural joint and monitor them through regular underwater inspections using remotely operated vehicles. Corrosion is another battle that never ends. Seawater is one of the most corrosive environments on Earth. The primary defense is thick protective coatings on all steel surfaces. But coatings are imperfect and can be damaged, so a second line of defense is always employed: cathodic protection. Blocks of zinc or aluminum alloy, called sacrificial anodes, are attached at regular intervals to the submerged structure. Because zinc and aluminum are electrochemically more active than steel, they corrode preferentially, protecting the structural steel around them. A large fixed platform may have thousands of individual anode blocks, each slowly sacrificing itself to preserve the structure. It is an ancient and elegant piece of electrochemistry deployed at enormous industrial scale in one of the harshest environments imaginable. The history of offshore engineering is also, unfortunately, a history written partly in disaster. The Alexander Keeland platform collapse in 1980 killed 123 people when a fatigue crack propagated from a weld flaw and caused one of the platform's 5 supporting columns to tear away. The Ocean Ranger sank in 1982 during a North Atlantic storm, killing all 84 crew members after a wave broke a porthole and triggered a chain of events that caused the vessel to capsize. Each of these disasters was investigated with extraordinary thoroughness, and each led to fundamental changes in design standards, operational procedures, and regulatory requirements. The offshore industry of today is vastly safer than the offshore industry of 1970. Not because the physics has changed, but because accumulated hard experience has been systematically translated into better engineering and better practice. When a major storm approaches an offshore installation today, the response is coordinated, methodical, and practiced. Meteorologists employed by the operating company begin tracking the storm days in advance. The operations team assesses predicted conditions against the platform's design criteria. If forecasts exceed the platform's rated survival capability, evacuation orders are issued early enough to allow safe transport of all non-essential personnel. The platform may be shut in completely, with wells sealed and equipment secured, before conditions deteriorate to the point where those operations become dangerous. And then the platform waits while the storm does its worst. And the extraordinary thing, the thing that never quite loses its power to astonish even after you understand the engineering behind it, is that when the storm passes and the sea subsides, those platforms are almost always still there, still standing, still intact, ready to resume operations, battered and spray-scoured and vibrating with residual wave energy, but standing. The ocean is vast and ancient and powerful beyond easy description. It has been shaping coastlines and sinking ships for as long as human beings have been going to sea. And yet, sitting out there in the middle of all that fury, held in place by science and steel and decades of accumulated human ingenuity, oil platforms ride out storms that would have seemed unsurvivable to any previous generation of engineers. That is not luck. That is not chance. That is what happens when humanity decides that a problem is worth solving and throws its full intelligence at it, generation after generation, learning from every failure and building something more capable every single time.